You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Bias in AI is best understood as systematic error that produces outcomes skewed in favor of some groups while disadvantaging others. Unlike random errors, bias is consistent and predictable, often reflecting deeper issues in the data or design of a system. For instance, an algorithm that underestimates women's likelihood of success in certain jobs consistently creates unfair outcomes, even if unintended. These errors matter because AI decisions influence real opportunities and life chances. By recognizing bias as more than just technical noise, by seeing it as a distortion with real-world consequences, we better understand why fairness must be treated as a guiding principle in AI development. Identifying bias is the first step toward ensuring that intelligent systems serve everyone equitably rather than amplifying inequality. Algorithmic bias occurs not only in data, but also in how models are designed and optimized. The choice of objectives, parameters, and constraints can inadvertently favor certain outcomes at the expense of others. For example, if an algorithm is optimized purely for accuracy, it may prioritize the majority class in a dataset, producing unfair results for minority groups. This is often not a matter of malice but of misaligned goals, where efficiency is valued more than equity. Algorithmic design decisions, such as which features to include or exclude, play a crucial role in shaping fairness. By acknowledging that models themselves can introduce or amplify bias, developers are reminded that technical design is inseparable from ethical responsibility. Fairness as a principle in AI centers on the idea of equal treatment across individuals and groups. It means ensuring that outcomes are not systematically skewed against people based on race, gender, socioeconomic status, or other protected attributes. Fairness is more than an abstract ethical goal. It is the foundation of trust in systems that increasingly make consequential decisions. Without fairness, AI risks being rejected by the very societies it aims to serve. Defining fairness, however, is complex, as it may mean equal opportunity for some, equal outcomes for others, or proportional representation depending on context. This diversity of interpretations highlights the importance of clarity, dialogue, and context when embedding fairness into AI practices. Representation bias arises when certain groups are underrepresented in training data, leading to poorer performance for those groups. A common example is facial recognition systems trained mostly on images of lighter-skinned individuals, which then misidentify darker-skinned faces at much higher rates. This underrepresentation skews performance and creates disproportionate harm for those excluded. Representation bias reveals the importance of inclusivity in dataset design, ensuring that all groups are adequately captured and respected. It also highlights the connection between technical quality and social justice, showing that fairness in AI cannot be separated from the diversity of the data it consumes. Label bias occurs when the process of annotating data introduces subjectivity or inconsistency. For instance, in medical datasets, doctors may vary in how they classify symptoms or diagnoses, embedding human variability into the data. In other contexts, labeling may reflect cultural or institutional biases, such as categorizing certain behaviors as problematic based on stereotypes. These inconsistencies can skew AI predictions, reinforcing human errors rather than correcting them. Addressing label bias requires careful standardization, transparency, and often diverse input during the labeling process. It reminds us that bias is not only in data quantity, but also in data quality, where subjective judgments can ripple through to create systemic unfairness. Proxy discrimination occurs when variables that seem neutral actually serve as stand-ins for sensitive attributes. For example, using zip codes as predictors in lending models can indirectly encode race or income disparities, as neighborhoods often correlate with socioeconomic and demographic factors. Even if sensitive variables are removed, proxies can reintroduce unfairness through correlation. This makes fairness more challenging, as bias can hide in indirect features. Detecting and addressing proxy discrimination requires careful examination of the relationships between variables and outcomes. It highlights the subtlety of bias in AI, showing that unfairness is not always obvious but can be embedded in seemingly harmless choices. Intersectional bias refers to the compounding disadvantages faced by individuals who belong to multiple marginalized groups, such as women of color or people with disabilities in low-income communities. AI systems often struggle most with these intersectional cases, as datasets may lack sufficient representation to capture their unique experiences. For example, facial recognition models may perform poorly for dark-skinned women, reflecting both gender and racial underrepresentation. Intersectionality underscores that fairness cannot be assessed by examining attributes in isolation. It requires attention to how multiple forms of identity interact. Addressing intersectional bias pushes developers toward more inclusive and nuanced approaches that reflect the complexity of human diversity. Feedback loops of inequity occur when biased predictions reinforce existing disparities over time. Predictive policing is a striking example. If algorithms identify certain neighborhoods as high risk based on biased crime data, more policing occurs there, generating more recorded incidents which then feed back into the system as evidence of higher crime. This cycle deepens inequity and undermines trust. Feedback loops reveal how bias can become self-sustaining in AI, locking systems into patterns that worsen inequality. Breaking these cycles requires active intervention, such as auditing predictions, introducing fairness constraints, and continuously monitoring outcomes. Left unchecked, feedback loops illustrate how small biases can spiral into systemic harm. Facial recognition bias has become a widely publicized case study, showing how unequal error rates affect real people. Studies have found that these systems often misidentify women and people of color at far higher rates than white men. The consequences range from inconvenience to wrongful arrests, raising serious concerns about justice and civil rights. These disparities stem from both representation bias in datasets and flaws in model design. Facial recognition bias illustrates how technical shortcomings translate into social consequences, demonstrating why fairness is not optional but essential. Public awareness of these failures has also driven calls for regulation, showing how visible unfairness can erode trust in AI. Hiring algorithms provide another case study where AI systems designed to streamline recruitment ended up replicating bias. Some models, trained on historical hiring data, favored candidates who resembled those hired in the past, often disadvantaging women or minority applicants. Even when explicit demographic data was removed, proxies in language use or educational background reintroduced bias. These systems highlight the danger of assuming that AI is inherently objective. In reality, it reflects and amplifies human choices embedded in training data. Hiring bias demonstrates the need for careful oversight and fairness checks before AI is applied in contexts that shape economic opportunity. Predictive policing offers a third case study, where flawed data reinforces systemic inequalities. Algorithms trained on historical arrest records often direct police resources toward neighborhoods already over-surveilled, perpetuating cycles of enforcement. Communities already marginalized become further stigmatized, while resources may be diverted away from areas with actual but underreported crime. This not only undermines fairness but also damages trust between law enforcement and communities. Predictive policing illustrates how biased inputs create biased outputs, which then reshape reality in harmful ways. It underscores the importance of questioning the assumptions behind data and the social contexts in which AI is deployed. The consequences of unfair AI ripple across legal, reputational, and human dimensions. Legally, biased systems may violate anti-discrimination laws, exposing organizations to liability. Reputationally, companies that deploy unfair AI risk public backlash, loss of consumer trust, and damage to brand value. Most importantly, biased outcomes harm individuals directly, denying them opportunities, justice, or dignity. These consequences remind us that fairness in AI is not a peripheral issue, but central to responsible deployment. The cost of ignoring fairness is measured not only in lawsuits or lost profits, but in human lives shaped by inequitable decisions. Addressing bias is therefore both an ethical and practical necessity for AI's future. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Detecting bias in models is the first step toward creating fairer AI systems. This process often involves auditing both training data and outputs to identify patterns of inequity. For instance, if a credit scoring model consistently assigns lower scores to applicants from certain communities, auditors must investigate whether the cause lies in skewed datasets, flawed features, or algorithmic design. Detection methods include statistical tests that compare error rates across groups, as well as visualizations that highlight disparities in predictions. Importantly, detection is not a one-time event, but an ongoing process, as biases can emerge when models are exposed to new data or changing conditions. By treating bias detection as a continuous form of quality assurance, organizations can ensure their systems remain aligned with fairness goals over time. Transparency in how these audits are conducted builds trust and sets the foundation for meaningful corrective action. Pre-processing mitigation addresses bias before a model is trained, ensuring that data fed into algorithms is as balanced and representative as possible. This may involve resampling datasets to include more examples of underrepresented groups, correcting mislabeled records, or removing variables that act as proxies for sensitive attributes. For example, in a hiring dataset, developers might ensure that resumes from women and minority candidates are proportionally represented to prevent skewed outcomes. Pre-processing also includes techniques like data augmentation, which artificially expands datasets by creating new, diverse examples. While these steps cannot erase all sources of bias, they reduce the risk of unfairness taking root at the earliest stages. Pre-processing reminds us that the quality and inclusivity of inputs largely determine the fairness of outputs, making it a crucial phase in responsible AI development. In-processing mitigation focuses on altering the algorithms themselves to incorporate fairness constraints during training. Instead of optimizing purely for accuracy or efficiency, models can be designed to also minimize disparities across groups. For example, a predictive model might be penalized if its error rate differs significantly between male and female applicants, nudging it toward more balanced performance. This approach ensures fairness is embedded directly into the learning process rather than treated as an afterthought. In-processing techniques can be complex, as they require balancing competing objectives, maximizing predictive power while reducing bias. Yet they are powerful because they shape the very logic of how models learn. By designing algorithms with fairness in mind, developers send a clear message. Equity is not a secondary concern, but a fundamental performance goal. Post-processing mitigation occurs after a model is trained, adjusting predictions to better align with fairness standards. This approach is often used when altering data or algorithms is impractical, but outcomes still need to be corrected. For example, if a hiring model disproportionately rejects female applicants, post-processing methods can recalibrate thresholds to ensure fairer representation in the final shortlist. Similarly, in credit scoring, adjustments may be applied to equalize approval rates across groups. While post-processing does not remove underlying bias in the model, it serves as a practical safeguard, particularly in high-stakes applications where immediate fairness is required. It highlights the layered nature of fairness strategies. Some interventions occur before training, some during, and others after, all working together to reduce inequity in AI systems. Transparency plays a critical role in addressing fairness, as it ensures accountability in how AI systems are built and deployed. Documenting datasets, model choices, and outcomes allows stakeholders to understand where potential biases may arise. For example, datasheets for datasets provide detailed records of how data was collected, who it represents, and what limitations it has. Transparency also applies to decision-making processes, such as explaining why certain features were included in a model or how performance metrics were chosen. Without clear documentation, it becomes difficult to evaluate fairness or assign responsibility when harm occurs. Transparency is not only a technical requirement but also an ethical one, building public trust by showing that AI is developed with openness and accountability in mind. Explainability complements transparency by making AI systems interpretable for stakeholders who may not be technical experts. An explainable model allows users, regulators, and affected communities to understand how predictions are made, making it easier to identify bias and challenge unfair outcomes. For example, if a loan application is denied, explainability tools can highlight which factors contributed most to the decision, ensuring accountability. This visibility empowers individuals to contest errors and provides organizations with insights to refine their models. Explainability transforms AI from a black box into a system that can be questioned and understood, making fairness assessments more accessible. By demystifying AI, explainability becomes a practical tool for detecting and addressing inequity, reinforcing the principle that fairness requires not just technical accuracy but human comprehensibility. Governance frameworks establish the policies and practices that ensure fairness throughout the AI lifecycle. These frameworks outline processes for auditing data, testing models, and monitoring outcomes after deployment. For example, a government agency might require regular fairness audits for AI systems used in hiring or credit scoring, similar to financial audits in banking. Within companies, governance may involve setting up ethics boards or dedicated fairness teams that oversee AI projects. Governance frameworks embed fairness into organizational culture, ensuring it is considered at every stage rather than treated as an afterthought. By creating structures of accountability, they ensure that fairness is not left to individual discretion but becomes a shared responsibility. Regulators play a vital role in ensuring fairness by enforcing laws and standards that hold organizations accountable. Anti-discrimination laws, consumer protection regulations, and data privacy frameworks intersect with AI practices in powerful ways. For instance, regulations may prohibit models that disproportionately disadvantage protected groups, regardless of intent. Regulators also set guidelines for transparency, requiring explainable decisions in areas like credit scoring or employment. Their involvement ensures that fairness is not optional but a legal obligation. However, regulation must evolve alongside technology to remain effective. Governments face the challenge of creating rules that protect citizens while still encouraging innovation. The role of regulators underscores that fairness in AI is both a technical and a legal issue, demanding oversight beyond the organizations that build systems. Ethical AI by design emphasizes building fairness into development processes from the very beginning. Instead of retrofitting solutions after problems arise, teams adopt fairness as a guiding principle throughout the lifecycle. This includes setting ethical goals at project initiation, choosing inclusive datasets, and testing for bias at every stage. By embedding fairness into design, organizations reduce the likelihood of harmful surprises later. For example, developers of an educational platform might prioritize ensuring their system works equally well for students of different linguistic backgrounds, testing accordingly during development. Ethical design shifts the mindset from compliance to commitment, treating fairness not as an external requirement but as an intrinsic value. Human oversight remains essential in ensuring fairness, even as AI systems grow more autonomous. Experts provide context, judgment, and ethical evaluation that algorithms cannot replicate. For example, in a hiring system, human reviewers might evaluate AI recommendations, ensuring they align with organizational values and fairness standards. Oversight also provides a mechanism for appeals, allowing individuals to challenge automated decisions. While AI can handle scale and speed, fairness requires accountability rooted in human responsibility. Human oversight ensures that AI remains a tool guided by people rather than an independent arbiter of opportunity and justice. It is a reminder that fairness is not solely a technical problem but one that requires human empathy and ethical judgment. Community engagement adds another critical dimension to fairness by involving those most affected by AI systems in their evaluation. Engaging communities ensures that fairness standards reflect real-world concerns and lived experiences, not just abstract technical definitions. For instance, in designing predictive policing tools, engaging community members allows developers to understand concerns about surveillance and potential misuse. This participatory approach builds trust and ensures that fairness is not defined solely by developers or regulators but co-created with stakeholders. Community engagement highlights that fairness is relational. It depends on how systems impact people and how those people perceive their treatment. International perspectives on fairness reveal that cultural and legal differences shape how fairness is defined and pursued. In some regions, fairness emphasizes equal outcomes, while in others it focuses on equal opportunities. For example, European frameworks often prioritize protections against systemic discrimination, while U.S. approaches may emphasize individual fairness and accountability. Emerging economies may face additional challenges, such as limited datasets that reflect local diversity. These differences remind us that fairness is not universal, but contextual, requiring sensitivity to cultural values and legal norms. International perspectives also highlight the importance of global cooperation, as AI systems often cross borders and must navigate diverse standards. Corporate responsibility in AI fairness extends beyond compliance, requiring organizations to adopt principles of responsible innovation. Many companies now publish ethical AI guidelines, commit to fairness audits, and invest in diverse teams to reduce bias. These efforts signal to customers, regulators, and investors that fairness is a priority. Corporate responsibility also involves transparency in how companies deploy AI, from advertising to hiring. By taking ownership of fairness, companies not only reduce risks but also build competitive advantage through trust and reputation. In a marketplace where consumers and employees increasingly value ethics, corporate responsibility becomes a strategic as well as moral imperative. Future research in fairness focuses on developing better tools for detecting bias, refining fairness metrics, and creating algorithms that balance accuracy with equity. New methods are being explored to test systems under varied conditions, ensuring they perform fairly across groups and contexts. Researchers are also working on ways to measure intersectional fairness more effectively, capturing the complexity of real-world identities. The field is dynamic, reflecting both the rapid evolution of AI and the growing recognition of its societal impacts. Ongoing research ensures that fairness is not a fixed goal but a moving target, requiring continuous innovation and reflection. Building public trust is the ultimate goal of fairness efforts, as widespread acceptance of AI depends on confidence that systems are just and accountable. Trust is earned when people believe AI treats them fairly, respects their rights, and offers recourse when mistakes occur. Without trust, even the most advanced systems risk rejection or backlash. By prioritizing fairness, organizations not only fulfill ethical responsibilities, but also ensure the sustainability of AI adoption. Fairness becomes the bridge between technical innovation and societal acceptance, determining whether AI is embraced as a tool for progress or resisted as a source of harm. Bias and fairness in AI represent defining challenges that demand transparency, accountability, and active mitigation. Bias can arise from data, algorithms, or human assumptions, but its consequences are always real, shaping opportunities, rights, and trust. Fairness is not a single metric, but a guiding principle, requiring vigilance at every stage of AI development and deployment. From case studies in facial recognition, hiring, and policing, we see how inequities manifest and why they must be addressed. Solutions exist at multiple levels: data, algorithms, oversight, governance, and community engagement. each playing a role in creating fairer systems. For learners, the lesson is clear. Fairness is not optional, but foundational. The future of AI will be judged not only by its intelligence, but by its integrity. And ensuring fairness is the path to building systems worthy of public trust. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.